All right, chapter 7. We got to start off with radians. Maybe it's been a while since you learned about them. We need to know them well. So here's our circle. Okay. Obviously, what is this thing? Well, 360 degrees around it. It's equal to 2 pi times the radius. Okay, now what do I mean by that? Well, here's the idea. Okay, so 2 pi times the radius is the diameter of the thing, right? Or there's 2 pi times the radius, rather, is the circumference of this beast. Okay, well, what if we introduce a new topic called 2 pi times 2 pi? Well, okay, so what if I just said this? What if I said this is part way around a circle? Or that's all the way around the circle, rather. And if I said, well, what about 180? Okay, well, 180 degrees is equal to 2 pi over, or 2 pi r times, times half, right? And the idea here is when we do these things, what we said was, what we say back in the day when we first started doing these, if you remember back in pre-calculus or algebra 2 when you learned these, 360 degrees is equal to 2 pi radiuses, although you sound like an idiot saying that. For 360 degrees all the way around, that's if you laid it out, there's 1 radius, 2 radiuses, 3 and a little bit radiuses, 4, 5, 6.28 basically radiuses all the way around the circle. It doesn't matter how big the circle is, that's always true. So 180 is equal to pi radiuses, and we just start calling them radians after that. 90 is pi over 2. 45 is pi over 4, of course, etc., etc. Now, we're not going to get crazy with the pi over 3s and memorize all that crap. We're not doing that. Okay, but here's the thing to remember. Boom, boom, boom. This is the angle theta. This is r and this is s. So s is equal to r times theta. Okay. Well, if you think about this is rolling now. This is a tire rolling down the road. How far does it go in 1 revolution? Okay, well, in 1 revolution is equal to 2 pi radiuses. 2 pi radians, yes? And that's how far it travels. So then if this radius is 13 inches, then it's going to go 2 pi times 13, whatever that comes out to be in inches, obviously. If this was 27 feet, then it'd be 2 pi times 27. In other words, it matters what the radius is because that actually gives you a distance traveled. Okay, so a couple things we'll talk about in this chapter: RPM, revolutions per minute. Okay, obviously you're going to want to get those into revolutions per second. Obviously, because why? Well, everything we do is in meters a second and so forth. Okay. Now, what we will look at is we'll actually look at radians per second. And that's how we'll actually look at it. Okay? Because you tell me we're going 3 radians per second. What we mean is we're traveling at 3 radiuses per second, which is basically meters per second. Are you with me? Because that's what we're going to be traveling in. This thing here is called angular velocity. And it is omega. And it may not shock you to find out that omega, it looks like butt, by the way. Let me draw a little butt there, is equal to alpha times t. Alpha, of course, is angular acceleration. You mean like angular acceleration. You mean like radians per second squared? I do mean that. Wait a minute. Would it be true that this minus this over this is this? Yes. Yes, it is. OMG, Mr. Groom. That's great. And so you could also write it like that. Of course you could. Plus. Of course. Duh. Obviously. Wait a minute. Are all the formulas that we did in chapter 1 going to show up here as well? Yeah. You're going to have theta is equal to omega t. Yes. Theta, of course, is how many radians. This is a angular displacement. How many radians did you turn? Okay. Well, it's equal to omega t if what? No acceleration. just like before. This is x equals vt, obviously, right? And then you got your definition of acceleration. True dat, Holmes. Wait, what about this fella? Well, you know it is, bruh. You know it is, except that's alpha. You know. What about this one? Nope. 1/2 alpha t squared plus omega naught t plus theta naught, or something like that. It's exactly the same as we did in x's and y's. And yeah, I mean, everything is legit the same. Okay, that's it. Okay, it's not hard at all. Now you're like, Grim, is there a way that I can go between these angular measurements and linear measurements? Dude, bro, yeah, of course there is. Watch this. Theta r. V equals omega r. Nuh-uh, that's it? Bro, that's it. What about alpha acceleration is equal to alpha r? It's exactly right. And so you can always make those substitutions. Okay? You're like, can I go both ways? Yeah, absolutely, sir. Absolutely. So what about rotational, kinetic energy? Yeah, well, rotational kinetic energy, well, you're going, oh, isn't it 1/2 mv squared? Isn't that kinetic energy? Well, it is. But what if I'm just going around and around and around? It's a good question. What if you are just going around it? I don't know what that is. That's an E, bruh. I don't know. What? Wait a minute. That's 1/2 m. This is omega r squared. So this is really just 1/2 m omega squared r squared. That is correct. That is correct. Yeah, exactly right. Okay. And so we'll actually be looking at a bunch of these things. But here's the kicker, and this is where it gets really interesting. This piece here and this piece here, that R suggests that, you know, like for instance, you had a cylinder where the radius was constant, but that's not how it is in life. Sometimes you'll have a top spinning, wee, you know, wee. Or perhaps you'll have a ball. That's a sphere, and it's spinning. True dat. Wait, what if it's a football? Whoa, that's different yet, bruh. But yeah, true dat. It's spinning here. Wait, what if it was spinning on its side that way? Excellent question. What if? And so the mass is distributed differently, and so are the radiuses. And so something that we talk a ton about in this class, in this chapter, is called the, I'm going to die, the moment of inertia. And so what we're going to get away from in rotational stuff is just so much the mass, because like in a kinetic energy situation, my mass, it doesn't matter. My car is moving down a road, 100 kilograms or 1,000 kilograms, whatever, it doesn't matter. At certain meters per second, well, it doesn't matter because it's not going around some axes and it's not changing, okay? But that's not true in a spinning body. And so what we have is I is equal to the sum of the masses times the radius squared, sort of. Okay? And so what we end up with here is, I say sort of, it is and it's not. Okay? So what we're going to end up with is 1/2 I and then omega squared. Okay, is what you'll end up with kinetic energy. But what do I mean by I? Well, I will be different from every situation. So, for instance, if you look in your book on page 175, if you have a solid sphere, it's not mr squared, it's actually 1/2 mr squared. If it's a solid sphere, it's 2/5 mr squared. If it's a hollow sphere, it's like 2/3 mr squared. And so it'll change based on what you've got in terms of how that is distributed. Okay, so what was the kinetic energy of a solid cylinder, solid mass of 60 kilograms, radius here is 0.3 meters, that's hot. So, and then turning that 50 radians per second. So the kinetic energy would literally be 1/2. Now a solid rod like that is 1/2. So it's 1/2 m 60 and then r squared. So this is 1/2 I and then omega squared. This is I. And the only difference between this and a sphere is this will be a different constant right there. That part would be different. You with me? So when I say it's sort of mr squared like that, it sort of, it depends on the shape because it has to do with how is that mass distributed. That's kind of a key feature. So 67.5 joules. Nice. So here's where it gets kind of fun, right? So some of that kinetic energy, if you like do this is a classic here. Woo, we did this earlier. We said, hey, listen, we get some up here at the top of the hill. It's got potential energy. We didn't roll it though. We just slid down the hill and it had kinetic at the bottom, right? True that. But in the case of a wheel or a sphere or whatever, it's got potential at the top. That is fact, Jack. Conservation of energy says, well, what's it got? Kinetic at the bottom. True, but what kind of kinetic? Well, it's going to have part of it is translational, so 1/2 mv squared. That's true. Plus 1/2 I omega squared, because part of it's going to be rotational. And depending on, what it's made out of, it's going to rotate at a different rate. Now, the question is, when I do this problem here, again, I has to do with m. You with me on this? So if a guy takes that into consideration, I is always going to be something, some constant, m omega squared, or mr squared, rather, mr squared. Sorry about that. What you can actually do then is just lose the m's. In other words, it doesn't matter what this sucker weighs because it's simply a matter of just dinking around with this thing and solving it out. So it's going to be 1/2, whatever the constant is. We'll worry about that in a minute, r squared omega squared. Okay? So I didn't tell you how this wheel was set up. This is it's just a hoop. It's a hoop, like a hula hoop, Groom. Correct. Does it matter what its mass is? Sure doesn't, clearly. This hill, 10 meters high. Nice. And away we go. So a solid, this hoop, which is spinning this way, is literally going to be this I for this hoop is literally just mr squared. Nice. So this is just 1/2 I. What I is mr squared. So the m's cancel. I'm just this. Radius of the hoop, 1/2 meter. Nice. So here we go. So 9.8 times 10 equals 1/2 v squared. We'll leave that alone plus that. Plus 1/2 0.5 squared. And then omega squared. Now, what is omega squared? That's from radians per second, right? So if I were to tell you one of these two guys, I could actually solve it both ways. I think I will do it this way just for fun. How many radians per second are we turning? Because remember, V is equal to omega R. So we can change this up a little bit. So that's 98 is equal to 1/2. And then that's going to be 0.5 squared again. Omega squared again. Plus 1/2. Oh, look at this. 1/2. And so 1/2 and 1/2 is 1, yes? Nice. And so you've got 0.25 plus you get 0.5 omega squared equals 98. And that's going to be 196 is equal to omega squared. Omega equals 14 radians per second. How many RPMs is that? It's an excellent question. So a radian, so 14 times, so 14 radians, 14 divided by 2 pi. So that's 2.2 revolutions per second times 60, well, times 3,600 rather. This thing is turning at about 8,021 RPM. Yep. Nice. Yay. Okay, cool. We could do all kinds of them like that. We'll do another example off the homework here in a second, but that's kind of the game. Okay. Oh, good criminy. I'm gonna die. Okay. We will have several several videos this week is my plan. Okay, here are a couple of examples from the homework. In a good light, a golden eagle can detect a 50 centimeter hair at a distance of 2 kilometers. What is this angle in radians? Okay, meaning here's your eyeball if you're a bird. Okay, if you follow that out, boom, boom, this is a 2 kilometer radius. Yes. And then this is 0.5, no, 50 centimeters, 50 centimeters, right? 50 centimeters? Yes, 50 centimeters. Yes, that's right. That's what I said, 0.5 meters. So this is really 2,000 meters. Okay, so then theta is equal to S over R. Need a calculator. So 2.5 E minus 4 radians, or in other words, 0.00025 radians. I don't know why I put a G at the end of radians, but there you go. Hot. What about this feller here? A drill bit is turning a 6 millimeter diameter drill bit is turning how many RPMs? 1200 RPM. What is the linear velocity? I don't know. Good question. Okay, so what we know is this. V equals omega R. So V equals now 1200 rate, that's revolutions, so times 2 pi divided by 60, because we need to get down to seconds, minutes, seconds. We need to get down to seconds, correct? Oh, that's what happened on this previous problem. Sorry, something looked weird on this previous problem. Times, yeah, that should have been more like 8,021 divided by 60. So 2.22 times 60. That should have been 133 RPMs over here. Anyway, back to this. Yay! So every revolution is 2 pi radians, and then there's 60. So we're going to divide by 60 there. That will be my rate, my velocity, my radians per second. So 40 pi. And then the radius. So the radius is 0.003. Remember, this needs to be in meters per second. So this thing is going 377 meters per second. All right, that's it. Nothing to it. Okay. I don't know. What about this one here? So a wheel. No, I don't want to do that one. It's boring. A 7 kilogram bowling ball, 30 centimeters in diameter. So bowling ball, 7 kilogram ball, 30 centimeters diameter. That's a lot, by the way. Rolls at a speed of 5 meters per second. What is its kinetic energy? I don't know. Let's find out. Okay, so here we go. So if I do this problem here, okay, what do I know? Well, I know kinetic energy. 1/2 I omega squared. Okay. And so, sweet. So can I find omega? Yeah, let's start with omega. Remember, omega is V over R. So omega is equal to V or 5 rather over 0.15. So 33, so this is 33 squared. Because it's a solid ball, I got to go look that up. A solid ball, again, page 175. A solid ball is 2/5 mr squared. So 2/5 m r squared. So 1/2 times 2/5 is 1/5. So 1/5 times 0.15 squared times 0.3, no, times 33 squared equals 5 joules of energy. Okay, that's the game. Okay, now there'll be more to this chapter. It is the Olympics after all. So during the Olympics, of course, you're going to watch some figure skating because, you know, obviously. And in figure skating, of course, we put our arms in, our arms out, we speed up, we slow down. That's conservation of momentum. And so I'll have another video later this week about conservation and momentum and that sort of thing.